Hi everybody, I hope this video finds you well. In today's video, we're going to be finishing up section 11.1 from your textbook, which introduced us to the concept of sequences. To do this, what we're going to do is we're going to begin by taking a quick look at a sort of review example, just making sure that we're still comfortable with the idea of analyzing whether or not a sequence converges or diverges, and determining what the sort of limit of a convergent sequence is. Then we'll turn our attention to sort of classifying sequences in a couple different ways. We'll be talking about bounded sequences and monotonic sequences. This will lead us to the sort of major theorem of this section, which is called the monotonic convergence theorem. That monotonic convergence theorem is going to be absolutely essential as we continue on into section 11.2 and beyond, where we begin talking about series, but we'll also see that it allows us to answer some questions about recursive sequences. And after we've sort of looked at a couple examples of recursive sequences, that'll pretty much wrap up everything we need to say about 11.1, and then we'll be ready to move into 11.2 and our more extensive discussion of series rather than sequences. But for now, let's just take a look at examining some different sequences and trying to determine if they converge or diverge. So to start off with here, we've got 4 sequences. We're just going to try to figure out if each of these converge or diverge. And of course, for the ones that converge, we want to be able to give their limit. So for A here, we've got an equals square root of n over ln of n. You'll notice that I'm sort of omitting the sort of starting spot. So, this one would probably make sense to start from like n greater than or equal to 2, because obviously ln of 0 wouldn't make sense, and ln of 1 would be 0, which would mean a divide by 0. But again, for us, since we're interested in whether or not these converge or diverge, we're interested in their long-term behavior. So we are just going to assume that these start from the sort of first whole number that would make sense. So for A, we want to take a look at the limit as n goes to infinity of the square root of n over ln of n. We'll notice that this is sort of mixed. This is n to an exponent, and this is a logarithm. We'll also notice that right now, this is in an infinity over infinity sort of situation, because obviously as n gets larger, the square root also gets larger, and as n gets larger, ln gets very large. So since these are two different types of functions, n to an exponent and the natural log, and since it's an infinity over infinity, we'd probably like to use L'Hopital's rule. So what we're going to do is we're going to use a replacement theorem, and we're going to try to come up with a continuous function that matches this. So we'd be now doing the limit as x goes to infinity. And remember, this isn't just changing the letter. This is also letting somebody know who's looking at it that while this n is discrete, meaning it's going, 2, 3, 4, 5, 6, 7, etc., this x is continuous, so it's going through all the numbers, the decimals, the whole numbers, the rationals, the irrationals, everything. This is a continuous limit now. The corresponding function would, of course, be square root of x over ln of x, and of course that does make sense, right? I mean, if we're in the positive values, square root of x is well defined, ln x is well defined, and their ratio is well defined, so it is a continuous function. Now that we have it in terms of a continuous variable, we can go ahead and apply L'Hopital's rule. Limit x goes to infinity. We take the derivative of the top and bottom. The derivative of the top is going to be 1/2 and then 1 over root x. And that's, of course, just treating that as an x to the 1/2. And the derivative of ln x is 1 over x. Okay, this is a little bit messy, but remember, so when you have complex fractions, denominators can shift. So this 2 in root x can move down here, and this x can move back up there. So now this is the limit as x goes to infinity of x over 2 root x, which looks to be the limit, if we simplify, as x goes to infinity of root x over 2. Now, of course, as x goes to infinity, this goes to infinity. Dividing it by 2 isn't going to have any impact, so this tends towards infinity. So we can say, by replacement theorem, a sub n diverges to positive infinity. So this a sub n, our actual original discrete sequence, is just going to keep getting larger and larger and eventually diverge to positive infinity. All right, for b, we have this minus 1 to the n, 4n plus 2 over 2n plus 5. We should know that b sub n is an alternating sequence. Alternating sequences were something that were the sort of first thing that we've encountered that is unique to sequences. You can't really define an alternating function because minus 1 to the x is going to be undefined whenever x is like a even radical, like 1/2 or a quarter or something like that. So this minus 1 to the n makes sense because n is a whole number. So alternating sequences, as we discussed in the previous video, are really sort of unique to sequences. How do we analyze them? Well, remember we stated a theorem that said that the only way that an alternating sequence can converge is if its absolute value converges to 0. Otherwise, this minus 1 to the n is going to cause the alternating sequence to alternate or oscillate between two different values, and that means that its limit is not going to exist, which means it's going to diverge. So, to analyze this, what we're going to do is we're going to consider the absolute value of b sub n, and we're going to look at the limit of that. So we'll actually be looking at the limit as n goes to infinity of the absolute value, which is 4n plus 2 over 2n plus 5. Now, this is an infinity over infinity situation, but we can do this very easily by multiplying top and bottom by 1 over n. No need to use a replacement theorem. We can get limit n goes to infinity, 4 plus 2 over n, 2 plus 5 over n. Then, of course, these, because they're constants over something that gets very large, go to 0. So this is going to be 4 over 2, which is going to be 2. So the absolute value converges to 2. Does that mean that this guy converges? Well, no. Actually, by our theorem, we know that our original alternating sequence, is going to diverge because it's going to, in the long run, basically oscillate between positive and negative 2. So b sub n will diverge. Limit does not exist. Sequence oscillates between plus or minus 2. So while the absolute value of our sequence converges to 2, the actual sequence we were interested in, which is the alternating one, its limit does not exist, so it diverges. And the reason that limit does not exist is because the sequence oscillates between positive and negative 2. All right, for C, C is, we've got arctan of e to the negative n squared, so we just got to apply the limit here. Not an alternating one, so we can just do it directly. So we have arctan of e to the negative n squared. So if we think about what's going to happen here, as n goes to infinity, this e to the negative n squared, well, this negative n squared is going to approach negative infinity. So I guess this is approaching e to the negative infinity there. Now, if we think about that, right, e to the negative infinity, well, e to the x sort of looks like this, and if we're approaching to negative infinity, we're going this way, which means we're approaching 0 from the positive side. So this is sort of like arctan of 0 plus. And if we think about arctan, well, arctan sort of looks like that, and it has this, but we're approaching 0 plus, so we're coming in like that to here, so we're approaching 0. So this equals 0. So we can say that C sub n converges to 0. So this one, we're just sort of analyzing the composition, working from the inside. As n goes to infinity, negative n squared goes to negative infinity. E to the negative infinity approaches 0 from the positive side. Arctan of 0 basically is 0, so we know Cn converges to 0. For our last one, we have d sub n, which is equal to 3 cosine n pi. So we want to try to apply the limit as n goes to infinity of cosine, 3 cosine, what do we say, n pi? Well, we might be a little suspicious about this because the limit as n goes to infinity of cosine doesn't really sound like it's going to exist. If we actually think about what the sort of terms of this are, let's just imagine that we start with n is 0. So we'd have 3 cosine of 0, which means that the first value would be 3. Then at 1, we'd have 3 cosine of pi, which would be negative 3. And then at 2, we'd have 3, and then negative 3, and so on. Yeah, this should be pretty clear that this d sub n diverges since limit does not exist, right? This sequence isn't even changing. It's just going back and forth between 3 and minus 3 each time. So clearly, it's not headed to any one value. So this is an example of something that diverges because the limit does not exist. Okay, so there's just a quick review about sort of basic sequences, just because that's what we had been doing in the previous sort of section, previous video, so we should make sure that we just wanted to review that. All right, now we're ready to start classifying some special types of sequences. And this is going to be important because, as we sort of stated, we're trying to gear up for this really important theorem that applies to very certain types of sequences. So we need a couple definitions here. So we're going to give sort of 6 definitions, but the sort of last definition in each section sort of just summarizes these. So most of these are pretty straightforward, but we will do an example right away, just making sure we're used to this new terminology. So a sequence a sub n is said to be bounded above if there exists a value u such that the sequence is always less than u for all n. So in other words, bounded above just means that there's some number out there that your sequence never goes beyond. A sequence a sub n is said to be bounded below if there exists a value m such that a sub n is greater than m for all n. So in other words, you're bounded below if you can find some number that your sequence never goes below. And in general, a sequence is said to be bounded if it is both bounded above and bounded below. So if you have both of these qualities, we just call the sequence bounded. All right, similar, right? This sort of tells us, how big the sequence gets or how small the sequence gets or whether or not it always lives within some range, so the dots are always within some range. Now, this is going to be very similar to for functions. We're going to talk about increasing and decreasing. So a sequence is said to be strictly increasing if a sub n is always less than a sub n plus 1. So in other words, each time you take a step forward in your sequence, the sequence gets larger. That should make sense for why we call that strictly increasing. A sequence is said to be strictly decreasing if a sub n is greater than a sub n plus 1 for all n. So in other words, each time you take a step forward, each time you increase that index by 1, the sequence itself gets smaller. So in other words, each term of the sequence is smaller than the previous one. In general, we say a sequence is monotonic if it is either strictly increasing or strictly decreasing. So if you are one of these two things, then we call that a monotonic sequence. Now, as we'll see in just a moment, there are sequences out there that are bounded. There are sequences out there that are monotonic. There are some that are both. There are some that are neither. So these are just special definitions. We're not saying that every sequence fits in these definitions, but we want to be able to classify sequences according to these definitions. So what we're going to do is we're going to look at a couple examples here, where for each of these sequences, we're going to decide if they are bounded, then decide if they are monotonic, and finally determine if they converge or diverge. So we'll get some more practice also looking at their limits. Now, all of these are going to be pretty easy in terms of determining their limits, so they won't be sort of as interesting as some of the analysis that we did here, but I do want to just do that quickly just to get additional practice. Okay, for each of these, though, just to, again, sort of remind us about sequences, let's also just write out the first few terms of each of these. So in this one, if we started from, say, n equals 1, we'd have 1, 4, 9, 16, so on. So that's what this sequence would look like. It should be very clear, if we talk about whether or not this is going to be bounded, that these terms are just going to get larger and larger. So, in other words, there's going to be no upper bound for this. If you say that the upper bound is 100, well, if I pick n to be 11, I'll be at 121, and that'll be above 100. If you pick, say, 1,000 as your upper bound, well, at some point, n squared gets larger than 1,000, right? If we plugged in, 40, we know 40 squared would be 1,600. So I could always find a spot where my sequence goes above any number. So we should notice that this is not bounded above. Obviously, it actually is bounded below because it starts at 1 and just keeps getting larger. So, but overall, it's not bounded, right? Because to be bounded, you have to have both an above, a lower, and upper bound. In this case, it is not bounded above. There is no upper bound. It should also be very clear, just from looking at these terms, that it is going to be strictly increasing, right? Every term of this sequence just gets larger and larger. So that means that it is monotonic. And just to maybe keep that consistent, instead of saying that like that, we'll just say not bounded. Okay, so this would be an example of something that is not a bounded sequence, but is a monotonic sequence. Can we figure out the limit of this? Well, that should be very easy. Limit n goes to infinity, n squared is going to approach positive infinity, so a sub n would diverge here. Okay. And that should sort of make sense. If you have something that's not bounded above, meaning that there's no sort of cap, and it just keeps growing, then of course it's going to diverge to positive infinity. All right, let's look at this one here. So again, let's start by writing out the first couple terms. So again, let's imagine we start at n equals 1. So when n is 1, we get sine of pi over 2, which is 1. Then when n is 2, we get sine of pi, which is 0. Then when n is 3, we get sine of 3 pi over 2, which is negative 1. When n is 4, we get sine of 2 pi, which is 0. When n is 5, I guess we would get 5 pi over 2, which is coterminal with pi over 2, so it's going to be 1. And you can sort of see the pattern that this is going to continue. Okay, would this be considered a bounded sequence? Well, for sure, right? Sine is going to be bounded. It's never going to go beyond -1 and 1. So this is a bounded sequence. Is there a sort of unique bound? Well, you could say that there's tons of different bounds. You could say it never goes beyond -2 and 2. Or you could be a little bit more accurate and you say it never goes beyond -1.1 and 1.1. Or you could be really sort of broad with your bound and you could say it never goes beyond -100 and 100. Doesn't matter though. The point is that it never leaves this range of -1 to 1, so it is a bounded sequence. Is it a monotonic sequence? Well, you can see that on the first step, it's a decrease, then a decrease, but then an increase, then an increase, then a decrease. So it is not strictly increasing, nor is it strictly decreasing. So this is non-monotonic. So this is an example of a bounded but non-monotonic sequence. So now we've sort of seen that these two are separate ideas because we saw one that is not bounded but it was monotonic, and now we've seen one that is bounded but non-monotonic. Okay, what could we say about the sort of limit of this? Well, it should be very clear that this is not going to have a limit. The limit is not going to exist. So the limit as n goes to infinity of sine n pi over 2 does not exist. So b sub n would diverge here. Okay. And the reason that that's not going to exist is that there's no one value that this sequence is headed towards. Instead, the sequence just keeps flipping between 1, 0, -1. It just hits those three values, never gets close to one single value. Remember, that's what a limit of a sequence means. Okay. For c sub n here, let's again assume that n starts from 1 and take a look at it. Notice that it's alternating, so it's going to go negative, positive, negative, positive. So it would be -1, then positive 1/2, then negative 1/3, then positive 1/4, so on. Well, is this a bounded sequence? Well, notice that its values here, it's never going to be like smaller than -2 because the negative components are like -1, negative 1/3, negative 1/5, negative 1/7, right? The negative numbers are getting very small. So it's certainly bounded below. And the positive values, 1/2, 1/4, 1/6, so on, those are also getting small. So this is definitely a bounded sequence. Is it monotonic? Well, -1 to 1/2, that's an increase, then a decrease, then an increase, then a decrease. No, right? It's not strictly increasing or strictly decreasing. This is, again, non-monotonic. So this one here has the same sort of properties as this, right? It's a bounded sequence, but it's non-monotonic. How would we analyze the limit? Well, since this is alternating, what we would do is, since it's alternating, right, we would consider absolute value, c sub n. We'd look at the limit as n goes to infinity. If we put this in absolute value, we're going to ignore the alternating piece and just focus on the 1 over n, and that is 0. So the absolute value converges to 0. We said that if the absolute value of our sequence converges to 0, then the sequence itself converges to 0. So c sub n also converges to 0. So this is sort of interesting. What this tells us is that if we run into a sequence that is bounded and non-monotonic, we don't have any information because I just gave you guys an example where it was bounded, non-monotonic, but diverged. And now we just saw one where it's bounded and non-monotonic and it converges. So unfortunately, if something is bounded but non-monotonic, it could either converge or diverge. Okay. Let's look at our last two, and we'll see that these two sort of hint at the theorem we're about to prove. So for this one here, let's go ahead and write out the first few terms. So again, assuming n starts at 1, we would have 2 over 1, which would be 2. And then at n equals 2, we'd have 3 over 2. And then at n equals 3, we'd have 4/3, and then 5/4, and so on. Okay, is this going to be bounded? Well, certainly it's bounded above. It's never going to be bigger than like 3. And also, you can tell that it's always going to be positive, right? No matter what n I plug in here, it's always positive. So it's certainly never going to go below, say, 0, right? That's a nice trick. If you know something is always positive, then you automatically know that it's bounded below by 0, right? Because if something's always positive, it never goes below 0. So this is definitely bounded, right? Even though it seems like these are getting smaller and smaller, I know they don't get too small. They certainly never get negative, so it's definitely a bounded sequence. Okay. What about monotonic? Well, from 2 to 3/2, that's a decrease. From 3/2 to 4/3, that's a decrease. From 4/3 to 5/4, that's a decrease. So this one is strictly decreasing, meaning it is monotonic. So this is an example, our first one, that has both these new features. It is both bounded and strictly decreasing. Let's take a look at its limit. So if we looked at its limit, we'd be doing the limit as n goes to infinity of n plus 1 over n. If we just simplify that a little bit, we get limit as n goes to infinity of 1 plus 1 over n. And that looks like we get a limit of 1. So d sub n converges to 1. So we now have seen that when this one was bounded and monotonic, it converged. Okay, one last one just before we get to our big theorem here. So let's again assume that maybe n starts at 1. So this starts at 1/2. Then when n is 2, we get 1 minus 1/2 squared. 1/2 squared is a fourth. So 1 minus a fourth is 3/4. Then at n equals 3, we get 1/2 cubed, which is 1/8. 1 minus 1/8 is 7/8. When n is 4, we get 1/2 to the 4th, which is 1/16. 1 minus 1/16 is 15 over 16. Okay. Is this bounded? Well, sorry, let's not get ahead of ourselves. Well, certainly, this thing here is always positive, so it's bounded below by 0. And if we think about it, this is always a little bit negative, so it never gets above 1. So this thing is certainly bounded, right? It's bounded between 0 and 1 for sure. What about monotonic? Well, if we imagine 1/2 to 3/4 to 7/8 to 15/16, it's strictly increasing. And that's because this 1/2 n is getting smaller and smaller. So we're subtracting smaller and smaller pieces. So the overall result is getting larger and larger. So this is strictly increasing. So it is also monotonic. Okay, well, let's take a look at its limit. So the limit as n goes to infinity of 1 minus 1/2 n. Well, as we said, 1/2 is a base that is smaller than 1. So if you multiply with itself many, many times, this is going to go to 0. So this is going to equal 1 minus 0, which is equal to 1. So E sub n converges to 1. Okay, so this just gave you guys a couple examples of understanding bounded versus monotonic. You'll see that back up here, and if you play around with it, if you are one or the other or neither, things could converge, they could diverge, we don't get any information. But these last two show us something sort of very important, even though it's only 2 examples. These last two show us that things that are bounded and monotonic are going to converge. And we're going to actually state that as a theorem and prove it. And that's going to give us our monotonic convergence theorem. When you run into sequences that only have one or neither of these properties, well, then you have to just analyze them one by one. They might end up diverging, like this one, which was bounded but non-monotonic, or they might end up like this one, where they converge, even though it was bounded and non-monotonic. But in this very special situation, where you have both of these qualities, sequences are guaranteed to converge. So let's state that and prove it. So this is a big theorem because we're going to use it to wrap up section 11.1, and we're going to reference it constantly as we make our way through the rest of chapter 11. So this is what's called the monotonic convergence theorem, and you'll often see this referenced as the MCT, just so that we can sort of abbreviate it. What this says is that it says if AN is a bounded monotonic sequence, then AN will converge. So in other words, if you are both bounded and monotonic, you're guaranteed to converge. Now, first thing I want to note here before we start to prove it is we can rephrase this theorem sort of in cases, so like with a bit more detail. If an is strictly increasing, then we only care that it is bounded above, which should make sense. If your sequence is getting just larger and larger, then clearly it is automatically bounded below because it just is getting larger and larger. So all you really need is, if you know it's strictly increasing, then you need it to be bounded above. Or if you look the other way, if you know your sequence is just getting smaller and smaller, all you really need to show is that it's bounded below, because it is automatically, if it's getting smaller and smaller, bounded above. So you can sort of give this and sort of be a bit more specific. If an is strictly increasing, then you just need it to be bounded above and it'll automatically converge. Or if it is strictly decreasing, then you just need it to be bounded below and then it'll automatically converge. Also, just because, you know, we're sort of starting to see more theorems now, do be aware that this is a one-way theorem. What we mean by that is that this only reads in this direction, meaning if you know something is bounded and monotonic, you automatically know it converges. If you run into a sequence that is not monotonic or is not bounded, this theorem provides us no information. As we saw in situations back here, here was something that was not bounded and it diverged. Here was something that was non-monotonic and it diverged. But here was something that was non-monotonic and converged. So if you don't have both of these properties, unfortunately this theorem gives you no information and you just have to analyze it manually like we were doing. So that's what we mean by a one-way theorem. It just says that if you know these two things, you automatically get this conclusion. Otherwise, no information. So let's go ahead and give a proof for this. So in your book, so in textbook, they prove for an increasing and bounded above. So we'll prove the other part, right? Because we technically would need to prove both situations as described here, strictly increasing bounded above, strictly decreasing bounded below. Your textbook, they prove the case where it's strictly increasing and bounded above, so we'll do the other ones. So we will do the other case. So what we get to assume is we get to assume that a sub n is strictly decreasing and a sub n is bounded below. And what we need to show, so what our goal is we need to show that a sub n converges. In other words, limit exists. Okay? All right. So what we're going to do is we're going to start with this a sub n being bounded below. Since a sub n is bounded below, we know, and we're going to use a little bit of sort of logic notation. This backwards e means there exists. So we know there exists a lower bound m such that a sub n greater than m for all n. This upside down a just means for all. So this is what it means to be bounded below. We know that there's some number m such that our sequence is always greater than m for all n. Now what we're going to do is we're going to choose L to be the largest lower bound. So obviously, as we were talking about, right, when you're trying to come up with a lower bound, you can use lots of different things. If your sequence is bounded below by -2, then it's also bounded below by -1,000,000. So what we're going to do is we're going to choose L to be the largest lower bound. So the largest thing that still counts as a lower bound. Okay, so now what we're going to do is now for epsilon greater than 0, consider L plus epsilon. So we're going to have an epsilon greater than 0. That's sort of standard limit stuff. We just want something that's just a very small, infinitesimally small positive thing. And we're going to consider L plus E. Now, L plus E is going to be a little bit larger than L. So since L plus epsilon is a little bit greater than L, this implies that L plus epsilon is not a lower bound. So, right, we chose L to be the largest upper bound, so L plus epsilon is not a lower bound. Okay, why is that important? Well, since L plus epsilon is not a lower bound, this means our sequence goes below L plus epsilon at some point. Okay? So if it's not a lower bound, that means our sequence dips below it at some point. Okay? So say that this happens at little n equals big N, i.e. a sub big N is less than L plus epsilon. Okay. So what we've just said is, just to sort of recap, because again, this is a pretty theoretical proof so far. What we're saying is L is the largest lower bound. We went slightly larger than it, L plus epsilon. That meant that L plus epsilon is not a lower bound. If you're not a lower bound, that means your sequence must go below it at some point. In other words, our sequence dips below L plus epsilon. So we're going to say that that happens at some moment little n equals capital N. So in other words, a sub capital N has to be less than L plus epsilon. Okay, let's give ourselves another page. So right now, just to sort of rewrite our last thing. So again, right, a sub n is less than L plus epsilon for some n equals n. Okay, but at this point, if you go back and look at what we've done, all we have used so far is that an is bounded below. That's everything we've been using. We still have this assumption that an is strictly decreasing. So we're now going to make use of that. The argument here is that, but since a sub n is strictly decreasing, this means once our sequence goes below L plus epsilon, it must stay below L plus epsilon, which should make sense, right? If you dip below L plus epsilon and you're strictly decreasing, you have to stay below L plus epsilon. You can't go back up because then you wouldn't be strictly decreasing. So what this means is that instead of saying that a sub capital N is less than L plus epsilon, we can actually say a sub n is less than L plus epsilon for n greater than capital N. In other words, instead of saying that it happens just at one single moment, we can say that it happens at that moment and beyond. So I guess we can actually put a little equals there. So we can say that a sub n is less than L plus epsilon for n greater than or equal to n. Well, now rearrange this a little bit. An minus L is less than epsilon for n greater than or equal to n. And if we think about this, L is now the lower bound. It's not L plus epsilon. So we know that this side is always positive. So it's safe to just put it in absolute value. It won't change anything. So an minus L is less than epsilon for n greater than or equal to n. Now, this might not look like too much, but if you look back in your textbook or you go back to the video that we did for 11.1 part 1, you will see that this is the definition of what it means for an to converge to L. The difference between an and L is less than epsilon for any epsilon greater than 0 for any n beyond some capital N. So this is the definition of an converges to L. And that's exactly what we wanted to show. So you can put a check mark, put your QED, whatever you prefer. We did it. We proved that an will converge to L. Okay, now this is a pretty theoretical proof. Again, I would read the one that is for strictly increasing and bounded above so that you can sort of see a second run through of this in your textbook and also just sort of see it written out again. Are you going to have to sort of mimic a proof as formal as this? Probably not yet. More the ideas are important here about why boundedness and monotonicity tell us about convergence. So I'm not going to say too much more about this proof, but I would like to just give a quick visualization of what we just did. If you think about what we sort of did here, what we're sort of saying is if we have a sequence, so maybe we have some points, they're strictly decreasing, so they're doing something like this. We're saying, okay, maybe we know that there's some lower bound down here, M, and we're definitely sure that our sequence never goes below that. But then what we said is we can make this L that is the lowest one. So we sort of said, let's make L here. And we know that this one, even though it's a bit higher up, we know that our points, even when we continue them on, never go below this. And then we scooted it up just a little bit, and we said L plus epsilon. And we said that this cannot be a lower bound. So at some point, let me do this one in a different color here. This one is not a lower bound. So at some point, ours is supposed to dip below that. But then, remember, it can't go below this one. So it must go below this, but it can't go below that. Well, this L plus epsilon, we can scoot it as close as we want. So notice that that means it doesn't matter what happens back here, but eventually the points have to be sandwiched in here. They have to keep decreasing, because it's strictly decreasing, but they can't go below this. So that means there really isn't anywhere for them to go, except that they can sort of approximate or limit to that L there. And that's really all we did in this proof, except we did it very formally rather than trying to argue it from sort of a visualization. Okay, as mentioned, this monotonic convergence theorem, very, very important. We are going to use this to prove most of the major sort of results about series, starting from 11.2, 11.3, 11.4. So we'll use this quite a bit. Just remember, it basically is a one-way statement. If you are bounded in monotonic, then you can automatically conclude that it converges. If you are not bounded or not monotonic, this theorem gives us no information. For now, though, I'd like to wrap up section 11.1 by using this monotonic convergence theorem, not to prove any big results, but just to analyze a type of sequence we've been unable to analyze thus far. So let's take a look at an example here. We're going to return to a type of sequence that we talked about at the very beginning, which was what we called a recursive sequence. So remember, a recursive sequence does not give an explicit equation for the values of the sequence. Instead, it tells you how to get the next value in the sequence based on the previous one. So we didn't have a way of analyzing the limit of those, but now that we have this monotonic convergence theorem, we are actually able to. So we're going to look at this example. We're going to consider the recursive sequence a sub 0 equals 16, and a sub n is equal to the square root of a sub n minus 1 plus 20. The first thing we're going to do, just to get a little practice, is write out the first four terms of the sequence. So let's start with that. So a sub 0 is 16. A sub 1, according to this rule, if you have a 1 as your index, then a1 minus 1 is going to be 0. So this would be a0 plus 20. And if you plug in a0 equals 16 in there, then that would be the square root of 16 plus 20, which looks like that's going to be the square root of 36, which is going to be 6. So ours goes 16, then 6. Then a2, I guess, would be the square root. If you have an index of 2, 2 minus 1 is going to be 1. So we have a1 plus 20, just the previous one. And that means that we would get the square root of 6 plus 20. So a2 would be the square root of 26. And since we wanted the first four terms, we've got 1, 2, 3. We just need to go one more. a3 would be the square root of a2 plus 20, which would be the square root of the square root of 26 plus 20. So that means that our sequence, at least so far, sort of looks like 16, then 6, then 26, and then the square root of the square root of 26 plus 20, and so on and so forth. Obviously, they're going to get much messier as we go on, because we're just going to get these sort of compounded square roots over and over again. So there's our first four terms of our sequence. Now, as sort of you can clearly see here, while the first couple numbers are easy, the rest are going to get very messy. So it's going to be very hard to try to come up with an explicit formula for a sub n, right? What do these ones actually look like? Instead, we're going to try to get around this by using our monotonic convergence theorem. So what we're going to do is we're going to prove that the sequence is strictly decreasing, and then we're going to prove that it's bounded below by 3. Once we've proven these two things, we can use the monotonic convergence theorem to prove that the sequence converges, because if you're strictly decreasing and bounded below, we automatically know that it converges. Once we know that it converges, we'll be able to use a little trick to find its limit. But before we can do that, we need to do these two proofs. You'll notice that we're going to say we need to use induction. Now, induction is a very important sort of mathematical proof technique. Hopefully some of you guys encountered induction back in like a pre-calculus course, but if you haven't seen induction for a while, or if you've never seen induction, before we jump into these proofs, we're going to talk just a little bit about induction. So induction. Induction is used when you need to prove something at many, many different places. In other words, it's used to prove things just like this. We need to show, for example, that our sequence is strictly decreasing. So we need to show that it's decreasing on this step, then the next step, that every step is decreasing. When we need to prove that it's bounded below, we need to prove that this thing is bigger than 3, then this thing is bigger than 3, then this thing is bigger than 3, then this thing is bigger than 3. In other words, induction is used when you basically need to prove an infinite amount of statements. Visually, the idea of induction is that you can sort of visualize it as an infinite staircase. So imagine you have this sort of infinite staircase. And just for fun, we'll put you here. Right, there you are. You're sad because it would sort of be annoying to have an infinite staircase, especially when the sort of idea of the proof is that you have to prove that you can climb that staircase, right? So maybe you have a friend that's saying, you have to prove to me that you're capable of climbing an infinite staircase. So one way you could approach climbing that staircase is you could take the first step, and then you could take the second and the third and the fourth and so on and so forth, and you could try to just climb it, but since it's infinite, you'll never finish, and that's not going to work very well. So instead, induction gives us a different idea. What induction says is that there's going to be two things we need to do. First, we're going to do what's called the base case. And the base case is going to be showing that you know, in our little metaphor here, how to step onto the staircase. So in other words, you know how to start climbing. So we call that the base case. Then, once you've shown that you can get onto the staircase, what you say is you allow your friend to carry you to any step they like. So they carry you up to step K, and they put you up at step K. So you don't climb up to step K, they put you at step K. And then you demonstrate that you know how to get to the next one. So you show that you can get to step K plus 1. And this is called the inductive step. So you get to assume that you're already here. So this is sometimes, that K is called the inductive hypothesis. So you get to assume you're at step K, and then you have to demonstrate how to take the next step up. Why do these two things show us that we can climb the entire staircase? Well, you're getting onto the staircase, and then since you know how to take one step forward, once you're here, you can get to here. Once you're here, you can get to here. Once you're here, you can get to here, so on and so forth. And this step forward applies everywhere because we're going to do it arbitrarily. Your friend gets to carry you to any step, and you have to demonstrate how to take one step forward. So basically, we're arguing that the way to climb an infinite staircase is to show that you can step onto the staircase and then take a step forward. Putting those two things together, you can go all the way up to the top. Okay, so let's see how that applies in our situation. We want to prove that this sequence is strictly decreasing. So we're going to prove via induction a sub n strictly decreasing. So we need to do our base case. It's always going to start with a base case. So the base case here would be that we need to show that the first step forward in our sequence is a decrease. So we need to show that a sub 0 is greater than a sub 1. How are we going to do that? Well, this is literally the first step, so we can just check. We wrote out the first few values. So our proof here is that 16, which is a sub 0, is indeed greater than 6, so we're all good. So the first step of our sequence, which is why we wrote out those sequence values at the beginning, is a decrease. So we've got our base case. So now we're going to do our inductive step. So for the inductive step, you're going to assume that this is true, that a sub k step is true. What does that mean for us? Well, we're going to assume that a sub k is greater than a sub k plus 1. So in other words, that this is a decrease. A sub k is greater than a sub k plus 1. So if you move forward one step, it decreases. We then need to show that a sub k plus 1 is going to be greater than a sub k plus 2. So in other words, if this step is a decrease, then the next step is a decrease. So that's what we need to show. So how do we actually do that? Well, the proof, this is always going to be very formulaic. We're going to start with this assumption. So we're going to start with our inductive hypothesis. This is what the inductive hypothesis is often referenced as. It's just that thing you get to assume. And now we need to get to this. So how do we get to the next step? Well, remember, we have this equation that tells us how to get to the next step. So we're going to follow this. And by follow this, I mean we're going to use order of operations. So when we plug in, when we did those calculations, the first thing we always did was add 20. So let's add 20 to both sides here. Is adding 20 going to change the direction of the inequality? Not at all. So we're going to get AK plus 20 is also greater than AK plus 1 plus 20. Then the next thing we did is after we added 20, we applied the square root. So is square rooting both sides going to change this? Well, the square root is an increasing function, right? The square root sort of looks like that, meaning that if this is larger than this, then the square root of this is larger than this. So we can apply the square root on both sides without screwing up the direction of our inequality. Okay. Now, why is this good? Well, what is the square root of AK plus 20? Well, if we look up, if we have AK plus 20, then that means that this index is K. Well, this index is always one higher, so this, by definition, is AK plus 1. That's how we get to AK plus 1. We take AK, we add 20, we square root it. That's how we get the next thing in our sequence. Over here, this has an index of K plus 1. So if you take the index of K plus 1, add 20, square root it, that's how you get AK plus 2. And there we go. We've shown that if there was a decrease on the previous step, the next step will be a decrease as well. Check. So, by induction, A sub n is strictly decreasing. So we've proven that our sequence is always going to be decreasing. All right. Now, this is probably a little out there, and if you haven't seen a lot of induction beforehand, but don't worry, because we're going to take a look at the next part of the proof, which is going to be very similar, and you guys are going to see that whenever you're using these inductions for these recursive sequences, the sort of format of this is going to be almost identical. So there's several in the suggested exercises you can try as well, just to get used to the structure of this proof. For now, though, we're going to move on to part C of this and try a proof by induction to show that it's bounded below by 3. So for C, we need to prove A sub n bounded below by 3. So we need to do our base case. So what would our base case be? Well, we need to show that the very first element, so A sub 0, is greater than 3. So in other words, that the very first element is bounded below by 3. The proof of that should be very simple. We just look back. What was A sub 0? Well, it was 16. So clearly 16 is greater than 3. Check. Now we're ready to do our inductive step. So for our inductive step, we're going to assume A sub k is greater than 3. So we're going to assume that at some moment in the future, we're still greater than 3. And we need to show that if we step forward, AK plus 1, that that'll also be greater than 3. So that's our inductive step. We'll go ahead and do the proof over here. For our proof, always start with your assumption. So AK greater than 3. And then just follow the order of operations of our recursive sequence. Add 20 to both sides. AK plus 20 must be greater than 23. Square root both sides. Square root doesn't screw up the order of the inequality. And then there we go. What is the square root of AK plus 20? Well, that's plugging AK in there, which means it moves the index 1 forward. So this is equivalent to AK plus 1. So we now know that AK plus 1 is greater than 23. Does that match what we were trying to prove? Well, not exactly. We were trying to prove that AK is greater than 3. But if AK plus 1 is greater than the square root of 23, the square root of 23 is close to 5. I mean, that's definitely greater than 3. So there we go. We've proven what we wanted to show, that AK plus 1 will be greater than 3. So, by induction, A sub n bounded below by 3. Okay, in just a few moments, we're going to do a second example to make sure we're comfortable with this induction, but I definitely want to wrap this one up right away because we want to actually see, I mean, so far we've done some interesting proofs, but we haven't actually seen how any of this helps us figure out the limit. So at this point, we're ready to move into part D here. So from part B, we know a sub n strictly decreasing. From C, we know a sub n bounded below by 3. Okay, so we know it's strictly decreasing. We know it's bounded below by 3. So we can say by the MCT, we know a sub n converges. Great. So if we were just interested in whether or not it converges or diverges, we would be done. We know that it converges. But we want to actually go a step further and figure out its limit. So let's see what we can say from this. Since a sub n converges, we know limit as n goes to infinity of a sub n equals some value. So we know that this has to be true. We're just curious, what is that L? So how can we find that? Well, remember, we have this expression. We have an plus 1, or sorry, an, excuse me. That's how we wrote it. An is equal to the square root of an minus 1 plus 20. This is our recursion. So let's apply the limit on both sides. So the limit as n goes to infinity of a sub n has got to be the limit as n goes to infinity of the square root of an minus 1 plus 20. And on this side, let's bring this limit in there, which of course you can do because square root's a continuous function. So we get the square root of the limit as n goes to infinity, an minus 1 plus 20. Okay, but we know that this is L. And we actually know that this is L. How do we know this? Well, this is the limit of the same sequence. It's just one term behind. But if you're racing off to L and somebody is one step behind you, they're also headed to L. These have to be the same limit. So we get L is the square root of L plus 20. Okay, why is this good? Well, this is just an algebraic equation. We can solve this. You square both sides. L squared is L plus 20. L squared minus L minus 20 equals 0. That's L minus 5, L plus 4 equals 0. That means our limit is L equals 5, or it could be negative 4. Well, we have two possibilities for the limits. How do we choose? Well, remember, we know that it is bounded below by 3. So our limit never goes below 3. Well, that means this guy is out. Since a sub n is bounded below by 3, L equals minus 4 doesn't work. So we can cross this one out, and we are convinced. So a sub n converges to 5. So this must be our limit. And this might be a little crazy here, but actually, if you think about this, this is an incredible result. Because what we've just done is we've figured out the limit of the sequence without even knowing what the values along the way look like. Because as we saw, even the fourth value is getting really messy with these compound radicals. So we've never figured out what the individual terms look like. Like, we don't know what a sub 1000 looks like. But we do know that a sub 1000 is going to be really close to 5. And we did that using this monotonic convergence theorem. Okay, let's go ahead and try one more of these just to really show you that even though we'll have a different recursive sequence, the structure is going to be very similar. All right, so let's go ahead and consider this recursive sequence. So we have a sub 0 equals 2, and then a sub n. So the way we step forward is we do 5 minus 4 over a sub n minus 1. And just to make sure that's clear, it seems like it's sort of misprinted a little bit there. This should be a sub n minus 1. So that's the previous term. Always got to have a recursive sequence involve the previous term. So we're going to write out the first 4 terms, prove that it's strictly increasing this time, prove that it's bounded above by 5. Once we've done these two things, we'll be able to use the monotonic convergence theorem to find the limit. So let's start with the first couple terms. A sub 0 is 2. A sub 1 should be 5 minus 4 over a sub 0, which is going to be 5 minus 4 over 2. And then that looks like it's going to be 3. Then a sub 2 is going to be 5 minus 4 over the previous one, a sub 1, which is 5 minus 4 over 3, which I guess if you made common denominators would be 11 thirds. And then a sub 3 would be 5 minus 4 over a sub 2, which would be 5 minus 4 over 11 thirds, which I guess would be 5 minus 12 over 11. So 55 minus 12, I guess that's 43 over 11. So this guy goes 2, 3, 11 over 3, 43 over 11. It's going to be pretty hard to find like a sort of pattern to that. But notice that if these are the two things we're trying to show, we haven't proven them yet, but it certainly seems like it makes sense. 2 to 3, that's an increase. 3 to 11 thirds, that's an increase. 11 thirds to 43 over 11, that's an increase. And none of these things are bigger than 5. So certainly these two seem to make sense. Okay. Let's go ahead and actually prove our pieces here. So we need to prove a sub n is strictly increasing here. So we're going to start with our base case. The base case here is we need to prove that a sub 0 is less than a sub 1. So this time we need to show that when we take our first step forward, it is an increase. Sorry, let's make that more how we did. Need to show, excuse me. And then our proof, well, this is why we calculate the first couple elements. We just need those first two. Certainly 2 is less than 3. Check. Okay. Now we can go to the inductive step. For the inductive step, we're going to assume that a sub k is less than a sub k plus 1. And we need to show that if we take another step forward, ak plus 1, it'll be less than ak plus 2. Okay. Let's go ahead and do that proof here. So start with your assumption, so ak is less than ak plus 1. And then we want to try to follow this order of operations. Notice that the first thing that we need to do is we need to have these be in the denominator. So we're going to do the reciprocal of each side. So that would be 1 over a sub k and 1 over a sub k plus 1. Now, if you think about the reciprocal function, 1 over x, that is a decreasing function. Meaning if you were larger than to start with, now you're smaller, right? If 2 is less than 4, then 1/2 is greater than 1/4. So the bigger you were originally, the smaller you are once you're done the reciprocal. So this is going to reverse the sign of the inequality. Okay? Then we want it to have a 4 in the numerator, so we can multiply both sides by 4. That's not going to change anything. Okay. But then we want it to actually be a negative 4, so we can negate both sides. Negative 4 over a sub k, negative 4 over a sub k plus 1. We probably all remember from basic algebra that multiplying both sides by a negative reverses the sign of the inequality, so now we're back facing this way. And then we add 5 on both sides. 5 over 4 minus 4 over ak, less than 5 minus 4 over ak plus 1. Clearly adding 5, not going to change anything. Why did I choose adding 5? Because that's in our formula there. Okay, now this right here is with a sub k plugged into our formula, so this is equivalent to ak plus 1. And on this side here, this is a sub k plus 1 plugged into our formula, so this is a sub k plus 2. We built the expression on both sides, so that means we can just rewrite them as the next step forward in the sequence. That's what we wanted to show. So a sub n, strictly increasing here. So we've proven again using induction. Notice it's almost identical because we're just sort of manipulating the inequality to build the expression for our recursion. So we know it's strictly increasing now. Okay, let's go on to the next page and prove that it's bounded above by 5. So see, we need to prove a sub n bounded above by 5. Okay, we got to do our base case. Base case should always be very straightforward. It's just based on the initial elements. We need to show here that the first value is less than 5. What was the first value? Well, it's right there. Our proof. 2 is less than 5. Check. Okay. Now we can go to our inductive step. So we're going to assume a sub k is less than 5. And we need to show that if you start off less than 5 and you take a step forward, you will still be less than 5. All right, we'll do that proof here. Start with a sub k less than 5. All right, we're going to go ahead and perform these operations again. So let's do the reciprocal. So 1 over a sub k must be greater than 1/5. Multiply both sides by 4. So 4 over a sub k must be greater than 4/5. Negate both sides. Negative 4 over a sub k must be less than negative 4/5. And then add 5. 5 minus 4 over a sub k must be less than 5 minus 4/5. We've built 5 minus 4 over a sub k, so we've plugged a sub k in here. That means it goes up 1 in the index. So that's a sub k plus 1. That's less than 5 minus 4/5. And of course, 5 minus 4/5, well, that is certainly less than 5. So we've shown that a sub k plus 1 is less than 5. Check. So a sub k bounded above by, or sorry, a sub n, we use k as sort of our single step, a sub n bounded above by 5. Okay, that's exactly what we wanted to show. So we can now go ahead and find the limit of this. So by MCT, since a sub n is strictly increasing and bounded above, a sub n must converge. So we now know a sub n must converge. Now, this is now, since we know that it converges, we can apply the limit. So remember, a sub n here is 5 minus 4 over a sub n minus 1. So we apply the limit. Limit n goes to infinity. A sub n, limit n goes to infinity. 5 minus 4 over a sub n minus 1. Same idea. If this is L, then when we apply this limit here, this is just the sequence one step behind. So if you are headed somewhere and your friend is one step behind you, they are also headed to the same place. So we get L is 5 minus 4 over L. We can go ahead and solve this now. Multiply everything by L. L squared equals 5L minus 4. L squared minus 5L plus 4 equals 0. Looks like we get L minus 4, L minus 1 equals 0. So the possible limits are 4 and 1. Well, we know we're bounded above by 5. Both of those are below 5, so unfortunately the bounded above doesn't help us. But keep in mind, we also know that we started at 2, and we proved that it's strictly increasing. So we started at 2, and we've been strictly going up, so that means this guy doesn't make sense. So a sub n converges to 4 since we started at 2 and increased, which means that there's no way we ended up at 1, right? If we had started at 2 and strictly decreased, then the limit could have been 1, but since we started at 2 and we're strictly going up, the limit must be 4. Okay, so this basically wraps up showing us a sort of really clever use of the monotonic convergence theorem. In the future, starting from our next section, 11.2, we'll be using the monotonic convergence theorem not to handle specific examples like this, but to help us prove results about the next type of mathematical object we're studying, series. But I did want you guys to see these couple sort of proofs, mainly because induction is such an important proof technique, and also because recursive sequences don't have any other real simple way of being analyzed. So it's a nice application of this theorem. For now, though, this wraps up section 11.1. In our next video, we'll be moving into 11.2, which introduces you guys to our next object of study, mathematical series.